journey into. This is the last set of our look at systems of differential equations, and we're going to have a look at what happens in the non-homogeneous case. So we've looked up till now at what happens when you're solving y dashed equals ay with some set of initial conditions, and now we're going to see the slightly more general situation where we have some sort of forcing term, some vector b of t added on to the system, and see what happens in this particular case. Now, the method employed here is known in the trade as variation of parameters. I'll explain what that means as we do it, but it's best seen by working through a number of examples. So I'm going to work through this example, and then I'll give you another one. You might like to try it yourself, and I'll go through that. And finally, I'll finish with a more serious 3x3 example. These ones, first two, are going to be just 2x2 systems. So what we have here is we have y1 dashed is 5y1 plus y2, plus we have this extra term on the end, 12e to the t. And similarly here we've got the simultaneous differential equations, but we've got this extra term added on the end, and there are the initial conditions. So here's the worked solution to this. And of course our first step always is to write everything in matrix form. So again, we're going to put vector y to be y1, y2, and then y dashed will be this matrix, the coefficients come from here, times y. And we've got this extra forcing term here, and I can factor out an e to the 12e to the t, and write this as 12e to the t times the vector 1 minus 1. And let me just note that equation. Of course, we've got initial conditions. Of course, y of 0 is the vector 2 minus 2. Now, this matrix A happens to have one sole eigenvalue. There's only one of them, and you can see then from the trace it must be 4. And the eigenspace for 4 turns out to be the span of minus 1, 1. And so the question, you can see, is slightly rigged because this vector here happens to be equal to or a multiple of the eigenvector. Doesn't have to be, it's more complicated if it's not, but here it's an eigenvector just to exemplify the theory. Now, the main step in solving all of these is to make this change of variable. We're going to put y is equal to e to the at times z of t. Now, it's called variation of parameters because if you look at the solution just of this equation here, then you know that the solution of this is y is e to the at times the initial condition, which is a constant vector. And so what we're doing is we're replacing the constant vector that we normally expect in our solution. We're replacing that with a whole function, which we don't know what this function is yet, but we replace it with a whole function. It's a technique that's often used in applied mathematics. If you know the solution of a homogeneous equation, then to get the non-homogeneous one, you try replacing the constant with a function. Anyway, that's called variation of parameters. Why do we do this? Well, you'll see in a second what it does for you. So I've got to substitute this back up into here, into y dashed is ay plus this thing. So I have to work out the derivative. I've got to differentiate this. Now I'm going to need to use the product rule because I've got two functions of t here. So I copy the first function, which is this matrix, and I multiply it by the derivative of this vector, which is z dashed. Plus I'm going to differentiate this matrix, and we've seen before, happily the a just pops down the front as it normally does with exponentials, and we just get a e to the at, copy down z of t. So that there is the product rule, or some version of the product rule, because we're dealing with matrices here and vectors. Now, on the other hand, on the other side of the equation back up here, we have ay, and I'm replacing y with e to the atz. So we get a e to the atz, that's my y in here, and then I copy this down, plus 12e to the t, 1 minus 1. Now the reason we do that is something beautiful happens immediately. This term cancels out on this side with this term on that side. And what we end up with then is e to the at times z dashed is 12e to the t times 1 minus 1. Now at this stage, of course, we don't know what z is and we don't know what z dashed is. So our plan of action now is going to be to try and solve for z dashed. Then we're going to integrate to work out what z is, and then we can plug the z back up into here and we get the final solution. So that's going to be our procedure from here. Now keep in mind what all these things mean. This beast here, of course, is some horrible big matrix we've talked about before. This is a very complicated large matrix, and I want to get this by itself, so I want to multiply by the inverse of this matrix. And as you might gather, of course, the inverse of e to the at is e to the minus at, and you can check that by simply, because a commutes with itself, you can simply multiply these together. That will give you e to the at minus at, which is e to the 0 matrix, and e to the 0 matrix is the identity. So you can easily check that these are inverses. So I multiply both sides by the inverse of e to the at, that's e to the minus at, and that'll recover the z dashed here. This is a constant, a scalar, so I take it out, 12e to the t, and then e to the minus at times this vector. And this vector, as I pointed out, happens to be an eigenvector. So we can now use our lovely theorem that e to the at times an eigenvector is e to the lambda t times the eigenvector. And I'm just replacing t with minus t. So I'm going to get e to the minus 4t, minus because of the minus here, and the eigenvalue is 4, multiplied by the eigenvector 1 minus 1. And I can combine these together, so I get 12 e to the minus 3t, 1 minus 1. Now that's z dashed, and I need to obtain z, so I'm going to integrate now both sides of this. I'm just going to integrate the 12 e to the minus 3t, so I'm going to divide by minus 3, that'll give me minus a quarter, e to the minus 3t times this vector. But when you integrate, you pick up a constant, which in this case is a constant vector, which I'll call c. So that's my constant of integration. Now if we go back and look at our substitution, we see that y of 0, the initial condition, is the same as z of 0, and we were given that that was equal to 2 minus 2. That was from the original problem. So we substitute that into here, so we get 2 minus 2 when I put t as 0. Put t as 0 here, I just get minus a quarter times this vector plus my constant vector, and I can then just subtract. So c is going to be this one minus this one, which turns out to be 1 quarter 9 minus 9, and I can happily take out the 9 as a common factor, and I get 9 quarters 1 minus 1. And so there's the constant. Okay, we're going to plug this back now up into my z, and that's what I do next. So there's the z of t is this expression. Finally, then, we need to remember we made this change of variable y is e to the at times z, so we can recover y by multiplying by e to the at. So I multiply this mess up here by e to the at. This is a scalar, so I can take it out, multiply the vector times e to the at. Similarly here. Now these are eigenvectors, and so we can use our theorem again, that e to the at times the eigenvector is e to the lambda t times the eigenvector. We do that in both places here, and I can simplify this a little bit and get down to here. So here is my solution, and from that I can pull off the two functions. I can read off the top line and the bottom line, and read off the two functions. So y1 is minus a quarter times 1 plus 9 quarters e to the 4t times 1, and then I'm going to get this times minus 1 and this times minus 1. And there are the solutions. And they are the two functions that satisfy the original system of differential equations, which is non-homogeneous. Now there's a lot of steps involved in all of these, so you might like to have a go at doing one yourself. Here is the example here. We're going to solve this system here. You might like to pause the video at this point and have a go at doing this one yourself, and then compare your solution to mine. But here is the word solution to this. So here is a system of equations. We immediately, of course, write it in matrix form, which looks like this. And here's the forcing term here. We get a 1 minus 3 times e to the 7t, and there's the initial condition. Now again, we analyse the matrix A firstly. So A has sole eigenvalue lambda equals 7, and the eigenspace just consists of 1 minus 3. Now again, we make this change of variable, and I've gone through the calculations again. So we differentiate the y. We get this by the product rule, so it's copy this one, differentiate this one, and then copy z and differentiate the e to the at, a e to the at, and that's supposed to equal to the matrix A times y, that's a e to the at z, plus the forcing term. And as before, these cancel, and I can get z dashed by multiplying both sides by the inverse of this matrix, which is e to the minus at, take out the scalar, and we get e to the minus at times 1 minus 3. Now once again, the question is rigged because this was an eigenvector. We saw up here, this was the eigenvector for lambda equals 7. So this is going to be e to the minus 7t, the minus because I'm replacing t with minus t. These cancel out and gives me this expression here. I can then integrate this, so I just pick up a t in this case, plus the constant. The y of 0 is the same as z of 0, and that was given by 1, 2. So the constant in this case is 1, 2. Plug that all back in. We get the formula for z now is 1 minus 3t plus this constant. Now this is an eigenvector, but this is not, and because there was only one eigenvalue, this one is going to be a generalized eigenvector. This is going to be in the next kernel out. So this is a generalized eigenvector, and so as usual we form a chain off this one. So we're going to chain in from 1, 2, multiplied by a minus 7i, we get 5 minus 15. I'll leave you to check the arithmetic. Now this has to be in the eigenspace, and it is. It's a multiple of this 1 minus 3 vector we had before. So if you do it again, you'll get nothing. Finally then, so we keep in mind our chain, finally then we want to recover our y, which is e to the at times z of t, and that's e to the at times 1 minus 3t plus e to the at times 1, 2. Now this one was an eigenvector, so e to the at times this is e to the 7t times the eigenvector, copy the t. And this was a generalized eigenvector, so we used the ideas from the previous chapter of what happens when you multiply e to the at times a generalized eigenvector. You get e to the lambda t, you get the eigenvector plus the next vector in the chain that we just got. Finally then, we can simplify this and read off what the solutions are. So we're going to get e to the 7t, we'll get a t there, we'll get a 5t there, that's 6t plus 1. And then for y2, we'll get e to the 7t, I get minus 3t, minus 15t is minus 18t, and then I'm going to get plus 2 there from this term. So they are the two functions that satisfy the initial condition and the non-homogeneous system of differential equations. So I hope if you did that one yourself, that's what you got as the answer. Just finally, just to show that you can do this for larger systems, take a deep breath, and I'm going to do it for a 3 by 3 system. Again, the arithmetic has been rigged in these to make it come out. In general, if you've got more complicated terms here, the calculations can be more complicated, but at least it's still doable. So here is our system, and we put it, of course, straight into matrix form, which looks like this. So here's our matrix. We get the coefficients from here, 180217, and e to the 10t into 0, 2, 2. and the initial condition y of naught is 1, 1, 1. Now this matrix A again happens to have sole eigenvalue lambda equals 8, and the eigenspace is 0, 1, 1. You change your variable as before. I haven't gone through all the calculations this time. I've just gone straight to what happens. You get e to the at times z dashed is e to the 10t times 0, 2, 2. Now this one is an eigenvector. It's just a multiple of this one here. So it's an eigenvector. So z dashed we multiply by the inverse of this matrix, e to the minus at. This is an eigenvector, so this is e to the minus 8t times the eigenvector as before, and simplifying gets me down to this. Finally then, of course, well, not quite finally, but we're now going to integrate this with respect to t. So I get e to the 2, so I'm going to divide by 2, I get e to the 2t 0, 1, 1 plus a constant. And we use the initial condition that z of 0 is y of 0 is 1, 1, 1. Plug it in, and I get the constant c turns out to be 1, 0, 0. Now this matrix happened to have only one eigenvalue and one eigenvector, so this one is going to be a generalized eigenvector, and so we can build a chain. We don't know what kernel this is in at this stage. We don't care really. The chain will tell us that as we calculate it. So 1, 0, 0 is a generalized eigenvector, so I start to chain in. So I multiply this by a minus 8i, I get 1, 0, minus 1. Now that is not an eigenvector, as I can see from here. So I'm going to multiply by it again. So in terms of the onion, we've got one eigenvector, we pick up one generalized eigenvector and one more. So this vector 1, 0, 0 is in fact in the outermost kernel, and we're chained into here, and we multiply a minus 8i again, and we land on this vector, and that clearly is in the eigenspace. It's just a multiple of this one, and we'll go to 0. So that in fact tells me that this vector was in fact in the outermost kernel. Okay, finally we get y. We're going to multiply the z by e to the at. So we get e to the 2t times 0, 1, 0, e to the at, and then e to the at times my c, which is 1, 0, 0. This is an eigenvector, so that is easy. That multiplies out to give me e to the 8t 0, 1, 1. And this is a generalized eigenvector, so I can use the chain. So this times this gives me e to the 8t times 1, 0, 0, plus this vector times t, plus this vector times t squared on factorial 2, which is just 2. I can simplify all this mess to get me down to here. So we're going to get two terms, and you see the solutions are starting to get more complicated. And then read off all the components. So y1 is just e to the 8t times 1 minus t. y2 is the second entry, which is e to the 6t minus t squared on 2 times e to the 8t. And y3 is one of these, and then I'm going to get minus t times e to the 8t minus t squared on 2 e to the 8t. And there is the solution to the non-homogeneous simultaneous differential equations using these lovely ideas from linear algebra. And that is the last video in this series of Journey into Linear Algebra.